All right, let's take a minute and go back to where we were before spring break. And for that, we need to review our intermolecular forces from chapter 6. So, if you recall, our intermolecular forces can pretty much be split down into two categories. There are the polar molecules and there are the nonpolar molecules. Now, how we evaluate polar versus nonpolar has everything to do with symmetry. And if you recall from chapter 5, molecules that are symmetrical, that have symmetrical shapes and symmetrical orientations of bonding groups versus lone pairs, those fall into the nonpolar category, and we'll talk about those in just a minute. Things that lack symmetry, things that are asymmetrical, either by the types of bonds that they have, so say substituting a chlorine in for a fluorine in an otherwise symmetrical molecule, or things that have lone pairs that create asymmetrical distortions. Those create small dipoles, small polarity that can be noticed in the molecule itself. And so we're going to start with talking about these polar molecules. And so from that standpoint, molecules that have permanent dipoles, that is, are polar, they're going to be able to interact with each other. They're also going to be able to interact with other ionic compounds. Now, the strengths of these interactions are kind of in between. They're weaker than ionic bonds. Ionic bonds are strong. We've got that electrostatic attraction between the positive cations and the negative anions, and that strength of that attraction really draws ionic compounds together and has them stick together really, really well. But for dipoles, we don't see that. We don't see that interaction even compared to covalent bonds. Covalent bonds are noticeably weaker than ionic bonds. And yet intermolecular forces, polar forces, are weaker than even covalent bonds are. But these polar interactions, this polarity that's caused by the temporary or rather the partial distribution of positive and negative charge between the positive pole and the negative pole of this dipole, those interactions between those poles and each other are stronger than what we get in nonpolar molecules on their own. So let's do a little investigation. So from a standpoint of dipole-dipole, we have substances here that have permanent dipoles, meaning we can see that there is a distribution, a distortion of electronic density here. And that distribution creates a slightly negative center and a slightly positive center on this molecule, whereas the evenness of the distribution here in the methylpropane creates no distortion whatsoever. And we can see that in the coloration here. This is a nonpolar molecule. This is a polar molecule. So the molecules that have permanent dipoles are going to have stronger interactions with each other. And those stronger interactions are going to impact their physical properties. And the physical properties we're going to look at in particular are boiling point, solubility, vapor pressure, and other things. Now, one particular type of polar interaction that is of note, and that is hydrogen bonding. Hydrogen bonding exists when we have polar molecules that contain an especially polar bond. And those polar bonds are existing between hydrogen and fluorine, hydrogen and oxygen, and hydrogen and nitrogen. So if I have a polar molecule that has one of these types of bonds in it, that particular substance is going to be susceptible to hydrogen bonding. And hydrogen bonding is going to have a stronger interaction than even polar molecules, dipole-dipole forces, will have. Now, it's still going to exist far below what we see for ionic compounds, but it is going to be different and it is going to be stronger. And these are the kinds of interactions that we actually see that hold together DNA, as opposed to covalent bonding, which is what people usually traditionally and erroneously think about DNA. The bonds that are holding together the guanine and the cytosine, the adenine and the thymine, those are hydrogen bonds that are being held between them, not covalent. Now, ions can also interact with dipoles. You've heard the concept of like dissolves like. Well, what that means is that polarity is going to attract other kinds of similar polarity. So ionic compounds that have charges in them are going to attract other molecules that are also charged. And so polar molecules like water, which exhibits not only polarity but hydrogen bonding, water molecules are going to be attracted to ionic compounds, and they're going to dissolve very, very well in each other. And when they do so, what we call those are ion dipole interactions. And these ion dipole interactions are a step above. They're kind of like a step in between polarity and ionic compounds. So really strong interactions taking place. And what we can also see, if we look closely, is that the way that these water molecules are orienting to the ions is different on each side. We can see that for the cation here, the positive ion is attracting the negative charges, the negative poles on each of these water molecules. Whereas the negative ion, the anion here, is attracting the hydrogens, which is the positive side of each one of these poles, and it's pushing away the negative side, the water side. And so these kinds of interactions are common, especially when we start thinking about ionic compounds, salts, being dissolved in water. Now, what about nonpolar forces? What about molecules that do not have dipole moments, that do not have that distortion of their electronic density? Well, in these, we have to look at something called London forces. London forces are the intermolecular forces that exist between nonpolar molecules, and they are caused by what we call temporary or induced dipoles. So if we can think about nonpolar molecules, we've got all these electrons and they're all kind of floating around inside of this molecule. As time progresses, there will come a point in time where the electrons are going to be unevenly distributed inside of that molecule. Just by random motion of the electrons in that molecule, we're going to see points where there are positive and negative sides. That's your temporary dipole. Now, the temporary dipole induces other dipoles in the molecules around it. Because when we have one side that is slightly positive and slightly negative, even if it's temporary, the lack of electrons on one side are going to attract more electrons to it from other molecules. And the abundance of electrons on one side are going to push other electrons in other molecules away. And that's going to induce dipoles in other molecules. And what we get through these temporary and induced dipoles, we get relatively small amounts of attraction that exist between the molecules that are near each other. Now, the property that is associated with the strength of these London forces is polarizability. And that is, how easy is it for electrons to get that distortion, to get to that point where we have uneven distributions on the molecule itself? And the answer there comes into one of two forms. We think of polarizability either in terms of size, where if I have larger atoms, larger molecules, we have more electrons available, and so just by sheer number, we're going to have a larger ability to distort that electron cloud and get more dispersion. Or by shape, where I have more increased surface area, and so therefore I get those molecules to be closer to each other, and I get more interactions that way. Now, how those work, so looking at the effective size, I can see here that as my atomic number increases for these atoms, I can see that the boiling point is increasing, and the boiling point is directly related to those intermolecular forces. The more forces there are, the more energy it takes to get those molecules to separate from each other, the higher the boiling point is going to be. So the more electrons I introduce, the more energy I'm going to have to introduce to get that substance to boil. Now, what if you don't have atoms? What if you have molecules? Well, we can estimate that using molar mass. And so from that standpoint, if we know we have nonpolar molecules, and all of these would qualify as nonpolar molecules because they are homonuclear, they have the same atom on each side, so they're going to share electrons evenly. We can see that the molar mass increase comes with a rise in boiling point as well. So there is a good solid relationship between the two. And so when it comes to size, if we're looking at atoms, yeah, we can look at atomic number, but we can also look at atomic mass as well. Molar mass is a pretty good indicator of size and the effective size on dispersion. And we can see this illustrated here as well, where we are going from a 1 carbon atom to a 2, 3, 4, 5, 6, 7, 8 carbon atom here, or 8 carbon molecule here. And as we increase in size, we see an increase in boiling point as well. Now for shape's a little bit harder to see. What we're primarily looking for is in organic molecules, we're looking for branching or lack of branching in the case of getting good dispersion. So here we have isomers. These are substances that have the same exact chemical formula, but are arranged in slightly different ways in three-dimensional space. And what we see is that the bulkier these are, so this is a linear molecule here. Linear in the sense it's a linear chain. The geometries of each of these carbons is still tetrahedral. But we have a linear chain here versus a branched chain, a fully branched chain here on the other side. And we can see that the more branching we introduce, the more bulky that this gets, the less interaction that the molecules have with each other, and the lower the boiling points get as a result. So shape doesn't always have it's not always a clear-cut kind of thing, but we can definitely see it happening more prominently with organic molecules where we have these kinds of isomer situations. And that's where we'll close this particular video. So our next video will recap and review intermolecular forces and physical properties, and then we'll also talk about phase diagrams to close out this particular chapter. So I'll see you next time.